Okay, here we go. It's been a long time since I made a video, so hopefully this all goes kind of smoothly. So section 2.2, adding and subtracting radical expressions. The key to adding and subtracting radical expressions is exactly how it's kind of noted right here. You need to have the same index and you need to have the same radicand. Okay, so the index and the radicand have to be the same in order to be able to add or subtract rational expressions together. This is our radical expressions. This is no different than trying to simplify polynomials. We know that 2x squared plus 2x squared is equal to 4x to x squared. The base and the exponent of the polynomial themselves are the same. These are like terms. We can add, we could subtract these if that were the function. Okay, so no different than adding or subtracting other polynomials together, or in this case, monomials. Okay, so the key is, well, sometimes these radical expressions are already with the same radicand and the index. Okay? So basically, as soon as you see a different index, then you cannot combine those together. But because we both have, because both of these, 5 root x and minus 2 root x, both of these are technically square root, okay, we can add these together. Simply we say, well, 5 minus 2 is equal to 3, and the radicand and the radical itself and the index would all stay the same. Nothing changes. So, and of course, we wouldn't write that with the 2 in there. 3 root 6. Okay. You're going to be given questions in which you have to possibly, with all of these, going to have to simplify these radicals before you can see that they can or cannot be added together, or in this case, subtracted. Okay, so the first step with question B, clearly we need to simplify these radicals. We've been working on that for a little while, so this should not be too bad. And again, you're going to simplify these radicals by whatever process you're using. Okay, you have a choice between those two processes. So because I can, I think I'm going to try and copy this, put it down here, so that I can work with it down here. Perfect. Question B. So, like I already said, you're going to use whatever process you're going to use in order to simplify these radicals. Sometimes you might be able to see that there's perfect roots within numbers, and you'll be able to pull those out. I can see that there's a perfect cube root within the number 16. That is 8 and 2. So 8 times 2 is 16. So this is the same as cube root of 8 times 8 times 2, which splits into the cube root of 8 times the cube root of 2. And then, of course, the cube root of 8 is 2. So this is 2 cube root, well, 3, but it should be a 2. Cube root 2, 3 cube root 2. This is that middle term. Okay. I chose that one because for me, I can see that that perfect cube within 16, so that was easy to do. But it's not something I would normally do. What I would normally do is do my whole prime factorization tree. So for example, let's do 28, 128. 128 splits up into 2 times 64. Now I can see it. 64 is 2 times 32. 32 is 2 times 16. And 16 is 2 times 2 times 2 times 2, which is 2 times 8. I follow the actual process properly. 2 times 8. 8 is 2 times 2, or sorry, 2 times 4. 4 is 2 times 2. So 128 is 2, 1, 2, 3, 4, 5, 6, 7. 2 to the power of 7, or 2 times 2, 7 times. So the cube root of 128, 2, 2, 2, 2, 2, 2, 2, 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. And remember, with cube root, you're looking for groups of 3. There is a group of 3. That's going to boot out one of my 2's. Here is a group of 3. That's going to boot out a second 2. And I'm left with my lonely 2 right behind. So that's going to be a cube root 2. We simplify these. coefficients now that they're outside the radicand. 2 times 2 is 4, so this is 4 cube root 2. That's my middle term. So there's not my middle term, my first term. I have my middle term. Now I need to do the same with my end term. And again, like I said, if you see the perfect root, go right ahead. If you don't see the perfect root, don't. If you can see this and go straight to, what is that, 27 times 2, 3 cube root 2, you're more than welcome to do so. If you make this mistake and you're asking me where it went wrong, I'm not going to be able to help you. Okay? So your choice. Okay? So some of the simpler ones you can see, the more difficult ones you can't. I would show some kind of intermediate step, even if you're just showing cube root of 27 times 2. At least I can see it. At least I see something. That would be best, would be optimal. Then I can see how you got to there. Or you're doing your tree. 54 is 2 times 27, which is 3 times 9, which is 3 times 3. This is 2 times 3 times 3 times 3, cube root of that. There's a group of 3. It gets booted out. 3. I'm left with cube root 2. There's my third term. Now I take those 3 terms, and in this case, I subtract each one of them. I go 4 cube root 2. That's that one. Minus 2 cube root 2 minus 3 cube root 2. Knowing that radicand and index are the same, I know I'm going to end up with a cube root 2. Has to be there. It doesn't disappear. So I go 4 minus 2 is 2. 2 take away 3 is minus 1. So I'm going to write minus 1 cube root 2. And if you just wrote negative without the 1 there, that is totally fine also. That's not a doctor marked mistake thing. Okay, that's number 2. Now let's do number 3. Or not, sorry, that was letter B. Let's do letter C. So again, I'm going to go like this. I can see it down here. Copy. Space. I lost space. Paste. Move it a bit. Go. There. Square root of 20 plus square root of 18 plus square root of 45 minus square root of 50. Again, if we have the same radicand and same index, we can do these subtractions. If we don't, we can't, right? So we can see that these are all square root. So if we can simplify these to all have the same radicand, we're going to be able to add or subtract these together. In this case, add, and then subtract. So again, going through whatever process you're going through to simplify, square root 20, I can see is 4 times 5. 4 is a perfect root. So the perfect root of 4 times 5. Perfect root of 4 is 2. So this is 2 square root 5. 18 is 2 times 9, which is 3 times 3. So this is the square root of 2 times 3 times 3. There's my group of 2. It comes out 3. I'm left with my root 2. Okay, so I did both of those each different way. So again, your choice on how you're doing these. The smaller numbers, it's easier to see. Maybe quicker for you to do the perfect roots. Bigger numbers, not as easy to see. So maybe off somewhere to the side, you're doing some scrap work and simplifying these radicals somewhere else. So 45, I know I'll do this one again like this. This is 9 times 5. 9 is a perfect root, so this is the square root of 9 times 5, or the square root of 9 times the square root of 5, which is the square root of 3. Sorry, not square root of 3, which is 3 square root of 5. And then square root of 50. 2 times 25 is 2 times 5 times 5. That's what's up. So that's the square root of 2 times 5 times 5. There's my pair. It gets kicked out. Left with square root 2. This is plus. This is plus. This is minus. So here you can see that this radicand and this radicand are different. So those cannot be combined. But, oops, 2 got erased. That radicand and index and this radicand are the same. So I can combine those. So 2 plus 3. 2 plus 3 is 5. And I keep my root and index and radicand the same. And then I see I can combine 3 root 2 and minus 5 root 2. 3 take away 5 is negative 2. So this is going to be minus 2. And the root and my radicand and my index, all the same, stays right there, 2. Okay. That's a similar process of kind of going like 4x plus 5y minus 2x minus 3y. Right? I can combine my 4x and my 2x because they're like terms. Gives me 2x. I can combine my 5y and my minus 3y. Gives me 2y. Okay? So just like that. That can't be combined any further. This cannot be combined and or simplified any further either. Okay, over the page. Simplifying expressions with variable radicands. Again, this is no different than what we've been doing. You go here, it's telling you, okay, we're going to have to simplify, right? Identify the values of the variable for which the radical is defined, and then simplify. So again, when you have variables inside the radical sign, you have to go through that process of defining the variables just to make sure. Otherwise, for example, 1 or letter A here, you could say, well, if x equals 0, or not 0, sorry, if x is equal to negative 1, then I can't do this question, therefore not possible. And then be done with like all of these questions. No point, would there? So we define these variables so that we can work through these questions, assuming that the variables aren't going to be those values. So as we did yesterday, we're looking at the variables within the radical and trying to determine what value in there makes it undefined. When we have the square root of a variable, x has to be greater than or equal to 0. We can't have a negative value in there. It's not going to work. So because all of these have the same index and radicand, we only have to do this once, and we simply say, well, x has to be greater than or equal to 0. And then we can look to simplify. So because this is already with an index of 2 and a radicand of x, these are the same, I can simply go 5 plus 3 is 8, minus 4 is 4. So this is going to simplify to 4 square root x, where x cannot be less than 0, so x has to be greater than or equal to 0. We say it kind of something like that. Somewhere if you've shown me this for this question, and this is an answer, that doesn't have to be lined up like this, but if this is an answer, then we're golden. And again, remember, this question could very easily just say simplify, but we still have to do the process of finding those defined values. Okay, moving on. Let me do this again. This. Copy, paste. Now we've got something to work with down here. Awesome. So again, we go through that process of defining our variables. In this case, we have 2 variables to define, so we have to do them individually. Again, remember, you can either take the term and isolate for the variable, or you can think through it logically. I think through it logically and kind of do the testing thing. So I can see straight away that these variables, or not the variables, the index and the radicand or whatever, in both of these, we have the a squared b term, a squared b term. So although these are going to simplify, they're the same so far. So I know that as soon as I do one of these defined variables, it's going to be good for the other term as well. I tend to do these straight away from the question. It's better to do that. You don't want to do this from a simplified version, because simplifying it may take away some possibilities that you may not see. So I think about the a term, the a variable itself first. What value of a can I put in there that's going to make this negative and make it not work? There isn't anything, because as soon as I square anything, I'm going to get a positive value, and a positive value can be raised to an even root. So a is one of those anything values. So a can belong to the set of all real numbers. B, on the other hand, B, if I'm testing, if B is 1, positive 1, this is all going to work out to positive. That's why I make this one. If B is positive, this is all going to work out to positive. Therefore, I can do the even root of a positive value. So B can be positive. If B is 0, this is going to work out to 0, so that's okay. But if B is negative, this thing, our radicand, is going to work out to be negative. I cannot raise a negative value to an even index. Therefore, B cannot be negative. So B has to be greater than or equal to 0. B has to be greater than or equal to 0. Yeah. I'm going to move that somewhere else. I don't like it there. A belongs to the set of all real numbers. B has to be greater than or equal to 0. Okay, so you're doing that somewhere. Maybe you're doing it right there. It doesn't matter to me. As long as you're showing me or stating what those values for those variables can or cannot be. Then we go through our simplification process, right? So if you're looking for the perfect squares, you can be doing it that way. I tend to try and shy away from the perfect square thing. I like the prime factorization tree. So I'm going to do exactly what I was doing before. I'm going to prime factorize 25a squared b. Well, 25 is 5 times 5. Those are prime. I don't need to go any further. And then my variables are a times b. Because we're doing square root, we're looking for groups of 2. There's a group of 2. 5 pops out. Here's another group of 2a's. A pops out. I'm left with my b, square root b. Similar process for the next term. So slide this over a little bit. I'm not, because that's not going to work. B. No, that's not going to work. B. Did the same process for this term. 4 is 2 times 2, and then I have a times b. That's square root. There's a group of 2. 2 kicks out. There's a group of 2. A kicks out, and I'm left with b. So with this term, I have, it's kind of messy, sorry, plus 2 square root 2a square root b. 2a square root b. Now I can see that my index radicand thing is all the same, square root b. So I can go 2a plus 5a. 2a plus 5a is 7a. 7a square root b. And again, remember also, similarly, if these coefficients aren't really the same, you're not going to be able to add them together, add or subtract either. So the coefficients also have to kind of, when there's variables involved, have to be able to combine, just like terms and combining any other variables. Okay, so let's do example C. Oops, that's the wrong tool. Copy, paste, move. There we go. Okay, so question C. Stating variables, stating our defined variables. So let's work on that first. So we have p cubed. We have p cubed here. In order for this to work, because we have an even index, this variable has to end up being positive. We can see that it's cubed, so that means that p has to be greater than or equal to 0, because if p was negative 1, this would work out to be negative, and then this would be negative, and you can't do the even root of a negative value. So p has to be greater than or equal to 0. Q, similarly, again, Q is raised to an odd odd exponent. Because it's raised to an odd exponent, Q can also or cannot also be negative 1, so that also has to be greater than or equal to 0. Because if Q was negative 1, this term would be negative, making my radicand negative, and then not being able to do the even root. So both P and Q have to be greater than or equal to 0. You can see the terms on the other radical, the other radical that we have to combine with are exactly the same. So our defined variables are now done. And again, you can simplify or write them somewhere else. P is greater than or equal to 0. Q is greater than or equal to 0. You could write that as one term if you wanted. P, comma, Q greater than or equal to 0. Some kind of combination of that. Your choice. Okay, so now we go through simplifying. We're looking for fourth root. So again, these are going to start to go fairly quickly for you for lots of work or lots of practice at this. The fourth root of 81 you probably know is 3. But if you don't, I can really quickly prime factorize 81. I know that that's like 3 times 27, which is 3 times 9, which is 3 times 3. Again, so I'm going to go 3 times 3 times 3 times 3. And then P, 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 Q, 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 Q. 3 P's, 5 Q's. And we're doing the fourth root. Because we're doing the fourth root, we look for groups of 4. There's a group of 4 3's. This 3 gets kicked out. I do not have a group of P's that is 4, so that stays. I have a group of 4 Q's. One of those Q's gets kicked out. Oops, wrong color, sorry. And I'm left with the fourth root of, what do I have left? P cubed and a Q. Similarly on the other one, prime factorizing this is going to be 3 P's, P, and then 5 Q's. And again, if you can see that you can pull out that Q without having to write your expanded, your repeated multiplication, that's totally fine. Pull it out. I'm looking, oh, it's not a cube root, it's a fourth root. Fourth root. Okay, there's a group of 4 Q's. It gets kicked out. P stays in. The Q remainder there, the last Q there. So the two terms I'm combining, 3 Q, fourth root, P cubed, Q, and is it plus or minus? It's minus. Don't forget, there was this 2 out in front here that gets multiplied to whatever we brought out. 2Q, fourth root, P, Q. Well, 3Q take away 2Q is 1Q. You don't have to write the 1 if you don't want to. Probably better if you don't. And then I'm left with, I keep writing cube root, fourth root of P cubed, cubed, cubed. Cubed, forgot the cubed up there. Simplified, and again, this one technically shouldn't be there. Final answer. Okay, then we go over the page to example 3. The only thing different now is we just start to get a little bit more complicated, maybe make you do a little bit more work to get some of these questions done, but same process. Okay, and you might end up with not double variables, 2 terms or multiple terms, just like we did up in question, I think it was question C up here. Yeah, question C. You might end up with a binomial, a trinomial. You might end up with terms that cannot be combined together because they're not like terms. Totally fine. Okay, so question number 1. Actually, what I'm going to do for all of these questions straight away before I forget is I'm going to very simply go through, oh, it tells me all my defined variables. Oh, nice. I saw the variables. I wanted to do definitions, but then I see they're right there already. Don't even have to do that. Perfect. Okay, so now I can go just straight to simplifying. So I'm going to combine some terms here. So if I'm looking at question A, this is square root x, this is square root x, so I can go 2 plus 5 gives me, I hear you all saying it, 7 square root x. And then I can go minus 3 with my root y and my plus 2 with my root y to get minus 1 root y. And again, you wouldn't write the 1 in there. Okay. Question B. Awesome. Again, we have our variables defined already. And just like question number 1, we have the same index, the same root, or same index, same radicand, and it's already simplified. So we can go straight to combining. So we have cube root 2x's and we have square root 2x's. Be careful that you're making sure that you see these. The index here and here are different than the other two. Okay, so I can combine, let's do this way. I can combine this term, 8 cube root 2x, and this term, minus 5 cube root 2x, 8 minus 5, let's go right down here. 8 minus 5 is 3. Don't forget the cube root 2x. And I can combine the other terms, 7 square root 2x plus 2 plus square root 2x, so just a 1. So 7 plus 1 is 8 square root 2x. Simplified. Done. It's nice when they're all simplified and ready to go for you. But most of the time, they won't be. Most of the time, you're going to have to look at these and say, hey, wait a minute. There's no terms that I can combine here. So I need to do my simplification process first. There. Copy this. I'm going to copy, I'm going to paste. And then I'm going to work down here. Okay. So maybe you're doing the work, the body of the work for these questions right here with your question, totally fine. If you're doing some scrap work off somewhere else, make sure that that's handy, because if I need to see something to see if it's correct or incorrect or where you went wrong, I need to be able to see whatever process you're going through. Okay? I'll do these right here, right in the body of the question. 5 square root 8x cubed. I can see that 8 is going to simplify, not simplify. I can see that 8 is going to break down into 2 times 2 times 2, and x times x times x. Because I'm doing square root, I look for groups of 2. There's a group of 2, pops out. Here's a group of 2, pops out. So I get a 2, and I get an x, and I'm left with a 2, and I'm left with an x, square root 2x. So there's one term I'm combining. 2x square root 2x. Oh, no, I'm not. Hold on. My bad. I forgot this. Don't forget that 5 was out there too. So I got to multiply that. So this is 10x square root 2x. There's my first term. Same for my second term. Maybe you're going through the process of thinking about perfect squares. I can see the perfect square within 75 is 25. So this is going to kick out a 25 and 5. And then y squared, there is a perfect square within y cubed, is a y squared times y. So the square root of 25 is 5. Square root of y squared is y. And I'm left with a 5y inside my radical. Don't forget I need to multiply the 4y that was out there to begin with. So 4y times 5y is 20y squared, square root 5y. There's my second term that I have. I need to combine. This was my first term. I'm just circling these or indicating these so I don't forget them. So now you can see at this point that my final answer is going to at least have 2 terms, because those cannot be combined. Third term, -2 or -2 square root 27y squared. I do this using prime factorization. I know that 27 is 3 times 3 times 3. I know that 27 is 3 times 3 times 3, so I can just simply go right to that. And I know that y is 5y's. I'm doing square root, so I'm looking for groups of 2. There's a group of 2, kicks out a 3. Here's a group of 2, kicks out a y. Here's a group of 2, kicks out a y. So it's kicking out a 2. Sorry, not a 2. A 3. We'll read properly. 3 and a y and a y. And I'm left with a 3y inside my radical. Don't forget I multiply this by the 2, or the -2 technically. -2 times this, so it's going to be a minus 6y squared cube root 3y. There's my third term. And then I do the last one. Let's go back to red. Minus 3x square root 50. Square root 50. I can see that there's a 25, which is perfect square. So there's a 25 times 2, 25 times 2 times x. Perfect square of 25 is 5. That gets kicked out. I'm left with my 2x on the inside as my radicand. Don't forget I need to multiply by this minus 3 3x times this. So minus 3 times 5 is minus 15x square root 2x. Fourth term. So now I combine all my terms. And I'll just write it in one line so it's all neat and organized. Well, I wouldn't say neat. It'll be organized. 10x square root 2x plus 20y squared square root 5y minus 6y squared square root 3y minus 15x square root 2x. And you can see that the only terms I'm going to be able to combine are this last term and my first term. 10x minus 15x, both square root 2x. So remember, when we're adding and subtracting, these variables also have to be the same in order to be able to do that. Can't combine, although these variables are the same, the y squareds, I can't combine them because my radicals are not the same. Okay, so I go 10x. So I go 10x. Oops, I don't want 10x. 10x minus 15x is minus 5x square root 2x. And then my other terms. Plus 20y squared square root 5y minus 6y squared square root 3y. And you'd be done. Order, I wouldn't worry too much about order. If you get the order different than your workbook, then the order is different. So it can be written in a different order. We would tend to try and follow some of the similar rules to writing out polynomials in their order, but it's not necessary. In my mind, it's not necessary. Maybe in future math classes that you take later, but for this year, this semester, it's totally fine. Okay, hopefully that all made sense, because math makes sense, baby. If it didn't, you've got the opportunity to rewatch the video, and you know how to get a hold of me if you have questions. The questions out of the workbook are posted on the sideboard, so you should be able to tackle some of those questions. And yeah, we'll go from there. And we'll see you next time.